Alright class, this video is going to focus on atmospheric pressure. So let's define what that is and then think about the scale that meteorologists use to quantify pressure. Let's also consider how pressure changes with altitude and why that is, and let's discuss the physical operating principles behind a basic instrument that measures pressure, which is a barometer. Atmospheric pressure can be defined as the force per unit area of an air column that extends from the surface all the way to the top of the atmosphere. Now that's a bunch of fancy words. We're really saying atmospheric pressure is the weight of the air above us. Let's visualize this. So here's the surface, here's the top of the atmosphere, and here's you, the curious young student who took a meteorology class because you needed an LAC course and you're afraid of chemistry. The way that we can actually visualize the... Oh, thank you, student, but let's try to focus on this example. Don't worry about it. I love the enthusiasm. So as I was saying, if we could actually visualize all of the air molecules in the atmosphere above us, extending from the ground all the way to the top of the atmosphere, we'd see something like this. So if we could add up the total weight of all those air molecules, that would be the pressure that we observe at the surface in that location. That's what we call barometric pressure. Well, if barometric pressure is the weight of all the air above us, then I'm sure you're asking, what happens as we climb higher into the atmosphere? Well, assuming we have the means to do that, as we go up, we're going to notice that we're now climbing higher than a lot of the air molecules, so we're actually going to measure a lower atmospheric pressure. Okay, so we visualize this concept of atmospheric pressure, and we've seen that it's going to decrease as we go higher into the atmosphere. Well, this arises from gravity acting on that air column, because all those air molecules are being pulled in by gravity towards the Earth's surface, so most of them are going to be concentrated near the ground. And then as we go higher into the atmosphere, we're above more and more of those molecules, and thus we're experiencing a lower pressure and a lower density of the air itself. And not only is atmospheric pressure and density going to decrease with altitude, it's going to decrease exponentially with altitude. If we could visualize this, we'd see most of the air molecules concentrated near the surface, and then climbing upward, we would experience an exponential loss in the number of air molecules left at that altitude. So as a result, air pressure and air density drop off faster and faster as we climb in altitude. Now there are multiple ways that we can express pressure numerically. You've probably heard of pounds per square inch before if you've ever filled up a tire. Well, pounds is a force and square inch is an area, so pounds per square inch gives us a weight or pressure. Inches of mercury was the first unit of measurement in terms of pressure. We'll see why in a second. Scientists like to use pascals because that's our standard unit that we can use in many calculations, but meteorologists prefer to use millibars. We'll also see why this is in just a bit. If we average barometric pressure across the world at sea level, that average value is 1,013 millibars. This is known as 1 atmosphere. This mean sea level pressure value is the central value within this table in inches of mercury, pounds per square inch, and millibars. But if you consider the range of observed sea level pressure values across the globe over our history, you'll notice that those values only range from 25 to 32 inches of mercury and about 13 to 16 pounds per square inch. But in millibars, those values range from 870 to 1,086, giving us a much wider range. This is important because meteorologists like to associate different values of pressure with different types of weather. As a result, meteorologists like to use millibars. The instrument used to measure atmospheric pressure, or barometric pressure, is called a barometer, and the first such instrument was a mercury barometer. I could explain how it works, but I think this TED Ed cartoon does a much better job. Take a look.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
So there you have it. A mercury barometer is composed of a mercury dish and a vacuum tube, and as air pressure increases and pushes further down on the mercury in the dish, the mercury in the glass tube goes up, and we measure a higher value in inches of mercury. Unfortunately, a mercury barometer is very difficult to automate, and the mercury could kill you. So we've come up with a different kind of barometer called an aneroid barometer, and this uses small flexible metal capsules that are usually made from copper. And as air pressure changes, that'll cause the metal capsule to expand or contract. That expansion and contraction will drive various mechanical levers, and that'll move the needle on a numerical scale. So here's an example of an aneroid barometer. We also have digital ones nowadays as well. That's it for now. Until next time.